part, let us get to know what a stack basically is. A stack is a linear data structure, as was the case with arrays, or as is the case with the queues. Linear data structure generally means that you have some sort of association between the elements. Each element is associated with the previous element or the next element, as you'll be seeing in the coming slides, right? So it follows last in first out principle. That means the last element that goes into a stack would be the first one to come out of it, right? So similarly, we have the insertion as well as the deletion takes place from the same end. So this is to say that there is only one end from which the insertion as well as the deletion takes place. Obviously, we'll need a single pointer, which in this case is known as the top, which keeps track of the topmost item in a stack, right? So the common operations are push, which adds an element to a stack, pop removes the topmost element, and peek only views or shows the topmost element without removing it or without updating the top pointer, right? So how can we implement stack? We can do it using arrays or using linked list. So array part we have done also. You can find the video in this data structure playlist, and then you have the linked list implementation that we will be taking up right away. So before moving on to the implementation part, we will first see what is a linked list. Linked list is a linear data structure where each element is connected to the next and previous element, as I discussed a few moments back. Similarly, it stores elements in a chain-like fashion where each element points to the next element, right? That pointing takes place basically in terms of storing addresses of one another that we'll be seeing in the coming slides through C programming code, right? So similarly, linked lists store elements in random memory locations. Random memory locations means there is no need of contiguity, as is the case with the array. So array stores elements in contiguous locations. So if we have an array of say 10 integer elements, and hypothetically the base address, that means the address of the first element is 100, then we are supposed to find the next element 2 bytes apart, that is at 102. Next element at 104, next element at 106, and so on. Here I am supposing that each element takes 2 bytes, right? So in case of linked list, the elements are stored in random memory locations that need not be contiguous. So we'll be further explaining things in the coming slides. For the timing, let us move to the last point. Linked list allows elements to be easily inserted or removed without reorganizing the entire structure, right? So we can take an element in between without reorganizing the entire structure. Similarly, for deletion, we can delete an item or the element of the linked list in the middle without disturbing the organization of the entire structure, right? Things would get clear when we discuss the linked list in detail. For the time being, we will be concentrating on the topic at hand, which is the linked list implementation of a stack. So coming on to the implementation part. So before doing the implementation part, let us see some key concepts that we should know first before going on to the actual implementation. So the first one is the node. So what is a node? Each element in a linked list is called a node. So it basically has two parts, the data part and the link part. Data stores the actual data that needs to be stored, and then you have a link part which stores the address of the next element, which is generally represented by a pointer that we'll be seeing shortly. So as far as the implementation is concerned, we'll be using the services of a structure variable, which is a user-defined data type, just like a class. So here the structure consists of the data part and the link part. So you can see a pointer representation or the notation here. That means that this part or this part in the picture is basically a pointer. And pointer, you as you know, is a variable which stores address of other variables, and you assign a data type to the pointer of the variable of which it is storing the value of. So in this case, struct node type pointer means that this part or this part would be storing address of another struct node variable, just like the one defined here, right? Since each node is a composite a kind of entity wherein we have two components, one is the data and another is the link part, it makes it imperative for us to declare the variable as a composite data type. So structure here represents a composite data type which is itself made of further data types like int and the pointer part. So you can have many more uh, data items which are generally called members of the structure in case of a structure. So you can have a struct student, then you can declare int roll number and name and address, parentage, and etc. Those all would be referred to as the members of that structure student, right? Same way you can store the details of an employee, and we can call that struct as struct employee. Then you can have id, you can have the first name, last name, salary component, and the other associated things. So here also you have two members. One is the data part, as you can see here, and another is the link part that you can see it here, right? So what is basically a linked list? We can move on to that. So a linked list, as you can see here, so this is a node, this is a node, this is a node, and this is a node, and this is also a node, right? So here is the data part 10, 20, 30, 40, and 50, and this is the link part. So I have assigned some hypothetical addresses to each node. So here writing 111 here means that this node has been declared, or it would be accessible at the memory location of 111. Obviously this is a hypothetical value, right? So for understanding purposes I have written here 111 as the address of this node, right? So same way, this node has been declared at the address 222 and so on, right? Another thing that is important to mention here is that the link part generally makes a connection or the link to the next or the previous node. So here in this case, writing a 222 here means that this node is storing the address of this node, right? So that creates a link. So this arrow is basically an indication that this node is connected, or it is associated with this address. How? Because it has stored address of that node. Similarly, this node and this node are supposedly connected because this node has stored address of this nodes, and same way here also this 444 is being stored here, this 555 is being stored here. Now understand that this address, these are all addresses. So how they can be accessible? They can be accessed by using a pointer. So that pointer would be struct node type. So this 111 as an address is not address of some integer or character or a float variable, in which case I would have written an int or a float or a char here. So I hope you understood that. What does this struct node asterisk mean? This struct node asterisk means that these addresses, or the address that would be stored here, would be of some node. So here that has been vindicated or justified because I have stored this 222 here, which is the address of another node like this one itself is a node. right? So this is let us compare this to say the concept of the array. I have here declared an array of the type of integer, and supposedly I would be restricting my discussions to 10 elements only. You can have a bigger array also. So if I can draw it, so I have taken here the array with 5 elements: 10, 20, 30, 40, and 50. So here is the, as you may be aware of the fact that the individual array elements are accessed using a unique number which is known as index. So index starts from 0. So 0th cell would be this would be 1, this would be 2, this would be 3, and the process will go on. So here I have shown some hypothetical addresses, like if this element, the first element of this array is stored at 100, the next element would be stored at 102, next at 104, and so on. Here I have stored those elements 2 bytes apart because the array has been declared as integer, right? So supposedly here I'm assuming that the integer in most of the cases takes 2 bytes an integer value. So that is why, so this 10 would be stored in the memory at the byte 100 and 101. That is where the next element would start. That means it would start at 102 and it would take another byte at 103. Then we will have this 30 at 104 and 105, since each value would be spanning 2 bytes, being an integer array. So this is what I was referring when I told you that the arrays store elements in contiguous locations, which in this case isn't true. In case of linked list, even though I have shown them as being stored in the contiguous locations or the subsequent locations, which may not be the case. So if this 111 is here, this 222 may be at some other location in the memory. This 33 would be at some other. So it is basically this address which is being stored that is important to maintain an association between the nodes rather than having them in contiguous locations. So this 1 1, this 2 2, this 3 3, they need not be contiguous. They can be any locations in the memory. So important thing is to store addresses of one another rather than being adjacent to each other. Right? So coming to the memory allocation, this is in continuation with the key concepts that we are taking up. Right? We should know some things or some definitions first. Then we can move on to the linked list implementation. So you will have to be patient for a bit more till we reach there. So memory allocation basically is of the type of static memory allocation and the dynamic memory allocation. In fact, we will be doing things this way when we implement things when we implement stack using a linked list. But we need to know the associated concept sets well. So static memory allocation is done before the program execution, while as the dynamic memory allocation is done during the program execution. So if I say I declared a variable called a with a value of 1, it would be declared like this. So you have the name of this cell as a, 10 would be stored there, and this is a hypothetical address I am assigning. You can obviously take any value or the address for understanding purposes or for referencing purposes, right? So I'm saying that this a has been declared at 1 FFE location in the memory, and a value of 10 is stored at that location, right? So if I have another variable p, since you know that a pointer variable is prefixed with an asterisk sign, to mark it as a pointer, and pointer stores address of other variables. So that is what I am doing here. I am assigning address of A to this P. Now since I am assigning address of some variable, it makes it a pointer variable, or it makes it a point to declare it as a pointer variable. Second and the most important thing is that since I am assigning the address of an integer, since A is an integer variable, so if I am assigning address of an integer variable to a pointer variable, that pointer variable should also be declared as an integer. That I was alluding to in the previous slide, that if you are storing address of a structure variable, that pointer variable also should be declared as a structure variable, right? So since P is storing address of A here, which is an integer, so that way we need to assign P a data type of it, or it is to be declared as a integer variable or integer pointer. So if we can see pictorially, so we are seeing here that P has been declared and it is being allocated or declared at a memory location 2FFE. Again, a hypothetical value I am taking, but the important thing is, what are the contents of P? Contents of P are 1FFE, which is the address of A. So I am assigning address of A to P, right? This is very important in the context of what we will be discussing shortly. That is the implementation of stack using linked list, right? Right? So coming to the dynamic memory allocation, which is done during program execution. What does that mean? That means we'll have some sort of functions or the instructions which would be executed at runtime, and they would be doing the memory allocation part. So there is a function in C which is called malloc. Malloc means memory allocation, which allocates memory, right? And the quantity or the amount of memory that is to be allocated is written within the parenthesis. That means that the malloc function takes integer as an argument. Since 2, we cannot write 2.5. So it isn't float, it is basically integer. So if someone asks you what is the type of this argument which is being passed to malloc function, the answer is integer. So malloc simply means allocates memory, and malloc2 simply means that you are allocating 2 bytes of memory. Now what does this int a, when we do write int a, this also allocates 2 bytes of memory if we are assuming that integer takes 2 bytes, right? So this is doing the same. Malloc2 is doing the same. Then what is the difference? Difference is that here you have named that location as A, while as here you have allocated 2 bytes of memory, but you have not assigned a label or the name to those 2 bytes that you have allocated. So we'll be elaborating on things shortly. Let us move to this second example. So malloc4 means allocating 4 bytes. Why I'm writing 4? Here I am alluding to a integer declaration. Here I am alluding to a declaration of a float which supposedly takes 4 bytes, right? But generally we don't allocate memory dynamically this way. That means we don't write malloc and then some integer, random integer within the brackets. So you can have an argument of why not do malloc 3, which would supposedly do a memory allocation of 3 bytes. But 3 bytes is generally not a standard size, even though 2 and 4 are to some extent, right? So what is the point here? Point here is that you do memory allocation in terms of standard sizes or the data types. So I'll be replacing these numeric values with another function in C which is known as sizeof. So sizeof int gives you 2. So malloc 2. So it is equivalent to this, writing, but writing it in a standard way, right? So if I am declaring some float variable at runtime, kind of, That means 4 bytes I am allocating. So I can write malloc size of float, malloc size of char, and so on. And malloc size of struct node is no exception. In which case, the total size of the structure, if it is say x, so x bytes of memory would be allocated, right? So we'll be discussing that shortly. So for the time being, let us concentrate on this integer part or the float part, right? So if you are writing malloc size of int, it means memory allocation of 2 bytes would be done. If I write malloc size of float, it means a memory allocation of 4 bytes should be done, and same for a character. Now what is this p? As I discussed here, in this case, that you would be declaring memory, but you would not be assigning a value or a label to it. That is what we are doing here. If we write only malloc size of int, 2 bytes would be allocated, but there won't be any label which would be pointing to those two allocated or declared bytes. So this p would store the address of those two bytes that were allocated. Or in short, to generalize things, when we write malloc, we do the declaration of memory or allocation of memory, but the starting address is stored at the variable that you have assigned it to, right? So in this case, when I write p is equal to, it means allocation would be done and the starting address would be stored by p, right? Now to check your knowledge, what would be the type of this p? Data type of this p? It would be integer, because you are allocating memory to an integer data type, right? Or size of 2. So this p would also be declared as an integer, right? So it is kind of this sort of declaration would be perfect in this case also, right? So if you are doing malloc size of float, then this p would be declared as a float pointer, of course, right? Now coming to the dynamic memory allocation for a node. So previously you saw if we will have to allocate memory for an integer or a float variable or the basic types. Now for a structure, how the memory allocation would be done, right? So if you are writing struct node, so this basically is a structure variable consisting of two parts. The integer part is the data, and there is a pointer part. As you would be aware of the fact that any pointer variable takes 2 bytes to store. So 2 bytes of this and 2 bytes of this int. So that would be the total size of this struct node. So if we will write that malloc memory allocation is being done of what size of struct node. What is struct node size? 4 bytes, as we just discussed. So malloc of 4, that means allocation of 4 bytes should be done, and the starting address would be stored at sp, which is a pointer variable of the type of struct node. As I just discussed, that this sp should be the same, or you can take it as a trick that this sp's type should be same as what you are writing here, size of within the brackets. So within the brackets I have written struct node, so this sp would be a pointer of that type. Just like we in the previous example wrote int asterisk p, then we wrote size of int. So what is written here in the brackets should be the data type of this pointer, also in this case the node type, right? Now let's understand a bit further, right? So sp is a variable, a pointer type variable, which is supposed to store address of certain node, right? I leave this for the moment. So this SP has been declared at 3FFE, a hypothetical address. Now, when you did this memory allocation, so the memory allocation is done at this location, say 00FE. So what is the address of the allocated node, I would say node because there are two cells. It has been declared in this context, right? So this would be my data part and this would be my link part. So collectively, it is a node which has been allocated a memory of 00 FE or at 00 FE, of course 4 bytes, right? So the address of this node would be stored here. Why? Because I have assigned this by using this is equal to I have assigned this address to SP. So the contents of SP would be 00FE, which is the address of this allocated node. Right? Right? So 00FE. Now, how to access? I'm sure you would have already done this while studying structures. I'm just polishing the things off, right? So when you access certain memory location as far as this structure variable is concerned, you use the pointer, you use this arrow when you are doing dynamic memory allocation. That means when you have declared the memory for a structure variable dynamically, then you use this pointer operator. So SP means SP arrow data means what is SP here? SP here is the contents. Just like when we say A and we store 10 here, then we print A, it stores a it prints contents of that A cell, which would be 10 in this example. Similarly, when I say SP, it means 00FE, the contents stored at that location, right? So this means the data part of SP or 00FE, which would be right here. So I am assigning the data part of the 00FE memory location to 3, right? By virtue of this statement. Similarly, the link part I am assigning to null. This is how you do things when you have declared a structure variable dynamically and you are using pointers, right? So a structure node, struct node, and in which two members have been declared as data and link part. Here you can see it, the data part and the link part. I have declared a variable, pointer variable p also. So next, let us say we have a function called create ll or create linked list, right? So in which we are basically allocating memory to the node and storing the starting address at p, then asking user to enter data, and that data would be stored in the data part, and to the link part we would be assigning a value of null to begin with, right? Like this. So the data, say for example we have passed a value of 3 as an input, that would be stored here in the data part, and a null part would be assigned to the link part. Similarly, let us say we have a main function in which we are repeatedly calling this function as shown here till user continues to press Y. So as long as he or she presses Y, we'll be calling this function again and again. Let us say the user in this example presses again Y, so another node would be allocated and its data part and link part would be accordingly filled. Right? Same for this node, same for this node. Right? So in this case, we have allocated memory for 4 nodes. But is this a linked list? No. The answer is no. Why? Because we have just allocated the memory for nodes without actually making or linking them together. So if that was the case, instead of null in the link part, I could have the addresses of other nodes that would be seeing later, right? So for the time being, we'll be moving to the actual topic, which is to create a stack, right? Of course, using a linked list. So here we'll be uh, declaring or implementing the actual linked list, but it would function as a stack. So it would have all the properties of the stack, like the last in the first or so. To make things clear, if we are creating a stack with elements of 1, 2, 3, and 4, the data that is being stored, Once traversed or displayed, the data would come out to be as 54321. Right? So here, to begin with, we have declared a struct node, a data part, a link part, as discussed already. But in case of a stack, we know that we need the services of the top variable. So we have declared that pointer top, but with an initial value of null. Similarly, we might be needing services of some other variables like t and p that have been declared here. Right? So as far as the push function is concerned, as discussed already, it would be used to basically push elements or the values or the data to the stack. Right? You can of course pass argument here from the main function or the calling function. For the sake of simplicity, I have not passed that argument, but I am taking the data part here in this function, right? So let us check what the code says. Here I am allocating the memory for a node, and as discussed previously, I am storing the starting address at P. Now I am asking for the value, and I am storing at the data portion of the P. So P is the address of, say, this node or the node that would be allocated. So the data part would be filled with the value that would be entered by the user, and the link part would be storing top. Now what is the top here? Top is null. So in case of this example, the link part would be storing null, right? But the top would now be assigned a value of p. Let us get some clarification from this diagram. So suppose this first node has been declared at the address, hypothetical address 111. So P would be equal to 111. Top would be equal to null. Right? So suppose uh, after asking for the data from the user, he enters or she enters 3. So that 3 would be assigned to this data part. All right. To the link part, what would be assigned? Top. What is top? Null. So null would be assigned to this portion. Right. Remember, P is 111 in this case. So this last statement, top is equal to P, means that my top value would be equal to 111. Fair enough. Why? Because the first element, as you saw in case of array also, the first element was the topmost element because that was the only element in that array in that case. And here also, since we have only one element, that would be my top element, right? That I have shown it using this pointer here also, that your top would be pointing to 111. Now, let us say this function was called from the calling function again. So it would be allocating another node. At what address? 222. So this P would be now 222. You can write it down or remember things so that we can do the further processing. So P would be storing the address of the new node, or the new node has been allocated at the address of 222. So P would be 222. Then I would be taking up data. So this is that 5. Suppose I have entered or inputted 5. So 5 would be stored as data part. The next thing is that P is this 222. What would be P is link part pointing to top. Top, as you can remember previously when we visited this function last time, top was 111. So it still is 111. So what would be assigned here? 111. Because I am assigning the P is link part to top. Right? Just before exiting this function, I would be assigning top a value of 222 by virtue of this instruction, right? So at the end of this function, execution of this function, top would now point to 222. Again, fair enough, because this is my topmost element. That is what is being shown here. Same for this node, it would be allocated at 333, right? Its link part would be pointed to top. or we can say the previous top. Previous top was 222. Now this top would point to 333 by virtue of this statement, and the process would, of course, go on. So if I, as an example, allocate 5 nodes here, though, so this would be my fifth node, and top would point to this. This is where we will stop as far as the push function is concerned. So in this slide we have seen how elements are pushed and how top as a pointer is updated in case of stack implementation of using linked list, right? So what about displaying contents of a linked list or a stack? So we can take the example of the previous slide. Say we have the elements 3, we have the elements of 3, 5, 2, 8, and 4, right? So this would be my top most element, that is 5. 555 would be my top address, but the value stored at that location, at the topmost location, is 4. So if we can quickly go through the display function, first we need to check if top is equal to null. In that case, we will have a condition of under flow. So if you can remember in the previous slide, to begin with, top was null at the beginning of the execution, but as soon as we allocated nodes, then that top would point to the latest allocated node. Here in this example, you can see supposedly this node, which was allocated at 555 address, was the latest node to be allocated, and its address is being pointed to by top. So this if would not get satisfied in this example because we have top not equal to 0, but top is supposedly 555. So what needs to be done is that we need to traverse now the stack or the contents of the stack. So for that we are assigning the value of top to a temporary variable t, which we have declared already, right? So what would be t? T would be 555 in this example. Why am I assigning top to t instead of using this top? Because we want to basically preserve the contents of top, because we might need it in the future also. So we'll be assigning top value to t. Then we'll run a while loop, and in the while loop, the condition would be while t not equal to null, right? Till then, we would be printing the contents of t, what are the contents of data part of t. Now, what is the data part of t here? T is 555. What is the contents of the data part? It is 4, right? It is 4. So 4 would be printed. Next, what needs to be done is that we need to update this top pointer or the t pointer to the next node. How we can do that? We will say t is equal to t arrow link. That means t would be equal to, what is t? T is 555. What is the link part? At that 555, link part is 444. So that would be assigned to t. So t now would point to 444. And if we can go again to the while loop, it would be now printing t arrow data, which is 4 arrow data, or 444 arrow data, which is the data part of this 444, which would be 8, right? So that is what is being shown here. First we will have the 4 as data, which would be displayed, then 8 would be displayed, then 2 would be displayed, and then 5 would be displayed. Why? In the reverse order, because we are implementing stack. The last in first out principle would be exhibited here. That means this 4 was the last element that was supposedly pushed to this stack, and it would be the first element to be popped or traversed or displayed, right? Now moving on to the pop function. Pop, as you can remember, that pop removes the topmost element. So for the same example, for which top is equal to 555, this code would get executed. Of course, we'll again check the underflow condition. Then we will assign the data part of top, that means this 4, to V, and top would be assigned to T, the temporary variable. Now top would be advanced to the link of top. That means what is top arrow link? Top arrow link means the link part of top. Top is 555 and the link part stored at that location is 444. So now top would be 444. Why? Because we need to remove this node. This is what happens in case of pop. That means topmost element is removed. But of course, top should be pointing to the next contender, which in this case is this 444 uh, node, right? So then we are doing what? Freeing the T. What is in T? 555. Free is a function in C which frees up the memory or removes the or deallocates the memory. And then of course we will print the value which was at the top, the previous top, the original top. That means 555. That, if you can remember, was stored at V, right? So here 4 would be popped up, this 4, and this top would be advanced to this. That means if we say this is the topmost element, it effectively means that this node has been removed, which is what we did here in case of free T instruction, right? In case of peak, for the same set of values or the same linked list, we simply need to show the topmost element without removing anything, right?